and we'll go from there. So first one here was a region in space where there's a high probability of finding an electron is called an orbital. It's called an orbital. Very good. And next question was, progress was made in the development of quantum mechanics once it was shown that electrons in an atom have what kind of properties? In other words, we started moving along in our current theory, which is quantum mechanics, once we learned that electrons and atoms have what kind of properties. So we'll count down 5, 4, 3, 2, 1. And of course, this is wave-like properties. Talking about the Schrödinger wave equation. That's where we're going to start here today, is with the wave equation. And next up here, this was like from earlier in the semester. Please, please, please get this one right. An atom of lithium normally has how many electrons? Atom of lithium normally has how many electrons? And so we'll count down on this one. You should hardly even have to look this one up. Unless you just can't find it on the periodic table. And we'll count down. 5, 4, 3, 2, 1. Oh my goodness. This is like really disappointing. 3. Where do we get that number? Yeah, number of protons and number of electrons have to be equal. Okay, wow. I'm just like, I feel like going home and crying right now. Okay, it's 3, but it's a Monday morning. I got a whole week left, so. Wow. Okay, it's 3. So check your score, because I'll be checking it afterwards, and I'll see who did that to me. All right, or did it to yourself. Okay, so today we're going to take a look at your packets here, and we're going to complete, I think, pretty much the entire packet today, and talk about some of the properties of these orbitals and what they mean. And I don't think in this class on Friday I had them sitting out here, but what I have sitting out now are models of orbitals, and I'd like to just kind of remind you what orbitals are and what we came up with this idea. And the first piece here was our first question on the Socrative app today, which was that the Schrödinger wave equation defined these regions in space where there's a high probability of finding an electron and called them orbitals rather than orbits. Now, part of the reason for that is that if we were to go back to this model here, which is the Bohr model of the atom, this is way too predictable, and so scientists are trying to come up with a way to explain why we observed the line spectra. And what was wrong with this model? What were some of the problems with this model? What was it?
The proportions are wrong.
Proportions are wrong? Actually, the proportions were actually pretty darn good.
The distance between the waves.
No, well, okay, that was one wrong. That's actually the problem with the picture. Okay, so the distances were wrong, but that's actually not the problem with the model. Yeah.
It only applies to the hydrogen.
Okay, it only applied to all the hydrogen, exactly. And another problem is if an electron wanted to go from here to here, what couldn't it do? Could it go straight down, or could it exist anywhere in the middle? No, it couldn't. It had to do so immediately, and that's where the whole idea of the quantum leap came into place. It had to immediately transition from one to another. And so this idea of probabilities kind of addressed that, because these here now are 2 orbitals, and inside of here, we don't know the details by which electrons move. All we know is there's a high probability of finding them somewhere in this space. And now if electrons were to move from this orbital to this orbital here, we now kind of fuse these all together onto the same nucleus around the same XYZ axis. what we see is that these spaces now overlap in 3 dimensions. So if this one were to have a higher energy than this one here, all of a sudden what would happen is the electron that was in this type of orbital could move to this type of orbital, and we wouldn't have to worry about there being a lack of existence anywhere in the middle. They just go from being confined to one shape to being confined to another shape. And so again, rather than saying that they were in these specific orbitals or specific orbits like in the Bohr model, we envision them being probabilities of finding them in certain spaces, and again those spaces overlap. And we kind of made an analogy then where when we look at these, what we're looking at is kind of like perhaps throwing a whole bunch of pitches over a plate where there's a high concentration in the center, and then as we go out they get to be less and less probable. And so if this is where they are in this space 70% of the time, we might envision it kind of looking something like this, except these here are what are called 99% contours, and 99% of the time they'd be found somewhere inside of the space. But the details of which we don't know, other than it's more probable in finding them in certain locations. And then what we do is we kind of shade those spaces in. Areas where it's more densely shaded meant that it was more probable. Areas where it's less densely shaded is then where it is less probable of finding an electron. So that's a review of where we were last Friday. Any questions on the review? Okay, so today, here's the new piece. You notice now that we have different shapes up here, and all of these shapes here represent different orbitals. And there's 2 main things that go into determining the energies of electrons found in orbitals. And let's see what they are. First of all, we could have orbitals that are this size, probably about the size of a racquetball. We could have one the size of a baseball. We could have up to a softball, kind of qualitatively speaking. And so if we were to compare the sizes, which size do you think would have the most energy? One that's small like this or one that's large like a softball? Softball. Why would the softball one have more energy?
Because the electrons are moving more.
They're moving more. That's one thing, yep. But that's not the reason.
Because the electrons are further out.
The electrons are further out. And what implication does that have?
They have more potential energy.
Exactly. They have more potential energy. So remember when we talked about the wood block off the ground, the further that wood block is off the ground, the more potential energy that it has. And so we look at it in terms of potential energy, not kinetic energy. All right? So the larger they are. So the first space we'd say is that there's 2 main factors that determine the energies of the electrons found in the orbital. One of them is the size of the orbital. See, and one of them is the size of the orbital. Now the second one, notice that all of these orbitals up here have different shapes. So it turns out the second characteristic has to do with the shape of the orbital. Now to make that analogy here, I'm going to look at these vibrating strings. And if you were to pluck on a string, that string can vibrate a number of different ways. Any musicians in here? Okay, if we have a musician, if we were to listen to these 2, assuming they're at the same volume, what would be the difference in these 2?
Pitch.
Pitch, exactly. Now, can you sing?
Not very well.
Not very well. I can't very well either, but I'll give it a shot. All right. So, in terms of pitch, this one here would be lower. This one here would be higher. So lower would be okay. So 2 pitches like that. So we're not talking about volume or how loud it is. We talk about them in difference of pitch. Now we'll put some physics to that. But you talk about this in music. If you had a good music teacher, you talked about this in music. What is the difference in pitch, physics-wise, called? This one here has a higher frequency, yes. This one here has a higher frequency. Now remember, we label frequency with the letter. What letter did we use? We used nu, right? So we use nu to represent the frequency. And what we said was that the energy, how is energy related to nu? Was it a direct proportion or an inverse proportion? Now we're just totally guessing again.
Direct.
It's a direct proportion. As we increase the frequency, we increase the energy. Now, we can also talk about another physics property. If we start looking at this shape here, what does this start looking like? Stuff we just looked at last week. This looks like a wave. And so this here is a wave, this here is a part of a wave. Which one has a longer wavelength? Top one's got a longer wavelength. This one has a shorter wavelength. So what is the relationship between energy and wavelength? Was energy and wavelength a direct proportion or an inverse proportion?
Inverse.
That was an inverse. So we made this type of statement here, that energy is inversely proportional to the wavelength. Okay? So what we could say then when we look at this here is that this one here has a longer wavelength, so a longer lambda, but it had a shorter or longer frequency. Not a longer, but shorter frequency. And then down here, we said this one here had a shorter wavelength, but this one here would have a higher frequency. And I guess we wouldn't say a shorter frequency, we would say a lower frequency. That's what I meant to say, lower. Okay, and of course that has to do with the fact that C is equal to lambda nu. Well, if all of a sudden we come back here and start saying, well now, these vibrating strings look a whole lot like the difference in these orbitals right here. Okay, they start looking a whole lot like it. This one here, kind of like this one like this one here. And so all of a sudden now, if we say that this one here has a shorter wavelength and a higher frequency, in terms of energy, this one here must have what type of energy, more or less? More energy than this one up here. So in terms of shape complexity, this one here has a greater energy than does this one here. And if we then went and looked at these two shapes, these are both orbitals, which of these two would have a greater energy, do you think?
Right.
This one here on your right. So it turns out that the more complex the shape, we could say the more the energy, exactly. So two things go into determining the energy of an electron. Coming back here, they are the size of the orbital and they are the shape of the orbital. So again, the larger the orbital, we could say, what does it mean? More energy. The more complex the shape, what does that mean? More energy. So again, the complexity of the shape and the size of the orbital both go into determining their energies. And so you need to remember those two as we start looking at our electron configurations here towards the end of the hour. So now the Schrödinger wave equation, again, we're not looking at the details of it. We're not going to derive it in here, but you are going to be expected to know the outcome of the Schrödinger wave equation. And it turns out that the Schrödinger wave equation generated four quantum numbers, a set of four quantum numbers. They are n, l, m sub l, and m sub s. And here's the rules associated, and this comes from the Schrödinger wave equation. These are the rules for those quantum numbers. They are, first of all, the principal quantum number n. What this does is it determines the size of the orbital and defines what we call the energy shell. And according to the wave equation, n can have values of 1, 2, 3. It can only have integer values that start at the number 1. And these quantum numbers are a whole lot like the values we looked at in the Bohr model determining the distance from the nucleus. So you can kind of think of when n is equal to 1, that's a small energy level, then second, third, fourth. So again, as those values of n increase, so do the distances from the nucleus. The second set of rules here is for the quantum number L, which is called the angular momentum quantum number. And the angular momentum quantum number, this determines the shape of an orbital. It defines what we call the energy sublevel or subshell. And as is noted here, L can be any integer value that goes between 0 and n minus 1. And so what that means here, let's say that n is equal to 2. If n is equal to 2, according to these rules, L could have possible values of 0 and 0 and 1. Because again, the possible values of L could be any integer value between 0 and n minus 1. So L could be 0 or 1. If n was equal to 4, then L could have values of 0, 1, 2, or 3. So again, what the rules tell us is that L can have any values that go between 0 and n minus 1, and L determines the shape of the orbitals. So when L is equal to 0, they take on this shape right here. And when they take on this shape, we say that orbitals belong in an s sublevel. When L is equal to 2, they have this shape here. And we say that electrons are in a p sublevel. And so we describe this often as a dumbbell shape. Often describe it as a dumbbell shape. And then when L is equal to 2, we say electrons are in a d sublevel. And these here, these 5 here, represent a d sublevel. And now notice here, as the value of L gets larger, so does the complexity of those orbitals we're looking at. Okay? And in terms of the number of lobes, and by lobes we're talking about, like this one here has how many lobes? It has 2. The maximum number of lobes that we can have is like 2 to the L power. So 2 to the L power, in this case, if L is 0, 2 to the 0th power is 1. So this has 1 lobe. When L is equal to 1, 2 to the 1st power is 2. So these have a maximum of 2 lobes. When we have L is equal to 2, we say they're in D sublevel. 2 to the 2nd power is 4. So these have a maximum of 4 lobes. I don't have up here the F orbitals, but I think I put them on a link here. Here we go. So if we look at these here, we go to the F's. Here's what F orbitals look like. And we see now that there's a maximum of 8 lobes on something like this. And so on. So the different values of L, again, tell us which sublevel they belong to. Then from here we go on to the what's called the magnetic quantum number, which is m sub L. And m sub L defines what we call the orbital, specifically the orientation of the orbital in 3-dimensional space. And m sub L can be any integer value between negative L and positive L. In other words, if L is equal to 1, and we say it can be any integer value between negative L and positive L, then we can see values of negative 1, 0, or positive 1. What's most important, not so much to us here at the end, is the specific values of them, but actually the number of different values. How many possible values are there here for m sub L in this case? There's 3 different ones. And how many possible values are there for m sub L when L is equal to 2? How many different possible values here? There's 5. So we look at this and we say that there's 3 different values. And we look at this one, and what we should observe more is that there are 5 different values. And what's significant about that is that the number of different values that are possible tells us the total number of possible orientations there can be around the axis in 3-dimensional space. So if we went back to the case here, we're not showing this one, but if L was equal to 0, if L was 0, what would M sub L possibly be equal to here? In other words, if L is 0, M sub L could only have a value of 0, and that means it could only have one possible value. Well, what does that mean? Well, here's a case where L is equal to 0. And when L is equal to 0, M sub L could only have a value of 0. Therefore, it only has one possible value, and there's only one way to orient a sphere around a 3-dimensional axis. So that's what that means. We have one sphere, and there's only one way to orient that sphere around a 3-dimensional axis. When L is equal to 1, remember when L is equal to 1, that tells us that M sub L can have 3 different values. And when there's 3 different values, it turns out that there's 3 different ways you can orient this dumbbell around an X, Y, Z axis. One is along the X-axis, one is along the Y-axis, one is along the Z-axis. So there's 3 different orientations in 3-dimensional space. When we get up to L is equal to 2, then we say that M sub L can have 5 different values. And so if you look here, then we have a total of 5 different types of orbitals in 3-dimensional space. And if you look very carefully at these, you're going to begin to see that these do not overlap the same space in 3 dimensions. Even though both of these lie along the XY plane, what is the difference between these two? This one here, the lobes lie along the axes. Here, the lobes lie between the axes. So in terms of 3 dimensions, these do not overlap the same space in 3 dimensions. This one here is kind of a funky one, but again, the mathematics of this are predictive of the shape. You might say this little disk actually overlaps some of the same space in here, but when you start plotting them out in 3 dimensions, what you find out is they actually don't occupy the same space. There's some gaps and stuff in these here along the axis that are occupied by these here. So again, the 5 different orientations. Now, what do you suppose once we get up to L is equal to 3? When L is equal to 3, how many possible values are there for M sub L? There's going to be 7. So how many different types of orbitals will there be, or orientations, in an F sublevel? There'll be 7 different ones. So if we come back here and look at the F orbitals, what we'd see is that there's 1, 2, 3, 4, 5, 6, 7 different orientations in 3-dimensional space. So again, the total number of values of M sub L will tell us the total number of orientations in 3-dimensional space. Again, these are called orbitals over here, and orbitals within a given sublevel have the same letter designation as the sublevel. So in other words, orbitals that are in the p sublevel, these are called p orbitals. These are orbitals that are in the d sublevel, these are called d orbitals. So again, d orbitals are found in the d sublevel, p orbitals are found in the p sublevel, s orbitals are found in the s sublevel. Now as far as where the letters S, P, D, and F come from, these come from description of the line spectra. So when we looked at the line spectra in here, there's things like, I think P is primary, D is diffuse, F is fundamental. So they come from different descriptions of the line spectra that are observed. And then the last quantum number that's in here is what's called the spin quantum number. And this one is totally independent of all the others, but once we define n, l, and m sub l, then the spin quantum number can either be a value of a negative 1/2 or a positive 1/2. And this here is the main implication that we'd have, is that because they can have two different values, what this tells us is that an orbital will hold up to a maximum of 2 electrons. So whether I'm looking at this orbital here, which is a very simple one, or this one here, which is a more complex one, the maximum number of electrons that can be in this orbital is 2. The maximum that can be in this one is 2. And that's it. So again, the spin quantum number tells us, because it can have two possible values for a given set of n, l, and m sub l, means that each orbital can hold a maximum of 2 electrons. Any questions on that piece? All right, now we're going to fill in this table on the next page. And this table here now is going to show us how those electrons are arranged within the atoms and give us some rules. And we're going to start here by looking at the lowest possible value of n. The smallest value that n can have is how much? 1. And when n is 1, remember that L can go anywhere from 0 up to n minus 1. So what is the only value we can have here for L?
0.
It's going to be 0. And we have n is equal to 1 and L is equal to 0. We call this a 1s subshell. And we call it a 1s subshell because the letter n designates this value here, and the 0 designates the subshell. And we get that because of the fact that when we come back here, we said that when L is equal to 0, we are then in an S subshell. Then let's remember that M sub L can go anywhere between negative L up to positive L. What is the only value we can have here for M sub L in this case? How much? 0. Because it can only go from 0 to 0, which is 0. And since it only has one possible value, that means there's how many orbitals in this subshell? Just 1. And remember now, each orbital can hold up to 2 electrons. So we would put in a 2 over here. If we go on to a second energy level, this is now where we say that n is equal to 2. When n is equal to 2, what are the possible values for L? It could be 0 or 1. Well, let's stack these here, 0 and 1. And then we're going to draw a line and across here. And then we're going to make a distinction between them. If we want to give a subshell notation, this first one right here would be labeled as 2s. This one here would be labeled as 2p. And it's 2p because we say that when L is equal to 1, then we have a p sublevel. So then we start looking at the possible values of M sub L. Let's go right here. What are the possible values of M sub L? Right here. 0. And how about down here? Remember, it can go anywhere between negative L and positive L. So it could be negative 1, 0, and plus 1. So now if we define the number of orbitals in the subshell, how many possible orbitals can we have here? 1. And over here we'd have 3. We have 3 possible orbitals because we have 3 different values for M sub L. Number of electrons in the subshell. First one here would be 2. The next one would be 6. And 6 because, remember, each orbital holds up to 2 electrons. Any questions yet? We're not going to go in order, so don't fill out this whole thing. Okay, number 3. When we have n is equal to 3, possible values of L are
0, 4.
and 2, 0, 1, and 2. Correct. So now we'll go across here. Let's go down now. This first one is going to be 3s. Next is going to be 3p. Next will be 3d. And we get the d because of the fact that when L is equal to 2, we have a d sublevel. So now we start filling in values of m sub L. In this first one, possible values of m sub L would be 0. Next row.
-1, 0, +1.
There we go. And then the next row, -2, -1, 0, +1, and +2. So going down, we put in 1, 3, and what's next? 5. And put in a 5 because we have 5 different possible values of m sub L, which means we have 5 different orientations of orbitals in 3-dimensional space. And the number of electrons respectively would be 2, 6, and 10. All right, go down and complete them for 5, when n is 5. Okay, so when L is equal to 4, we are in a G sublevel. In fact, once we begin right here, starting with F, they go alphabetical. So it'll be F, G, H, and so on. But the first 4 come from description of the line spectra. So here's what the G orbitals look like.
Are there Z orbitals?
What's that?
Are there Z orbitals?
Good question. I don't know. There are G orbitals. And you can look at yours once I get mine up here. Recording. We are. Okay. So help me complete this. This is going to be 5F. Last one will be 5G. 5F is going to go anywhere from
-3,
to
-2, +3.
all the way to +3. And this one's going to go everywhere from -4 up to +4.
7,
7 and
9,
9 and
14,
and
18.
18. Any questions on these? All right. So now, what this takes us to is the next page where we started here today. And let me just ask again, how many electrons are in an atom of lithium? 3. And what do we look at? Number of protons, which is the same as the number of electrons if the atom is electrically neutral. So if you don't have your periodic table out, let's get your periodic table out. And we are going to write out here what are called electron configurations. Electron configurations. And the electron configurations represents the arrangement of electrons in an atom. And ultimately, this arrangement of electrons is going to help us determine why elements combine the way they do. And we're going to start by looking at the atomic numbers for each one of these. So we'll start with hydrogen. What is the atomic number for hydrogen? It's 1. So we'd say Z is equal to 1 in this case. Which means it contains how many electrons? 1 electron. And we write its electron configuration as 1s1. And as far as what these mean, here's what these things mean now. We don't want that. We'll just show that there. There we go. 1s1. This first one here represents the value of N, which of course is the energy level. This here represents the energy sublevel, or L. And this number here, this superscript, tells us the number of electrons in the sublevel. Or subshell is another term. Whether I use sublevel or subshell, they represent the same thing. And so what this tells us is that there's 1 electron in the 1s subshell. And we read it as 1s1. We don't read it as, it's not an exponent. So you don't say 1s to the first. We say 1s1 is the way that this one is read. So we go on to the next one. And we look at the element helium. Helium has 2 electrons. So with 2 electrons, we'd write its electron configuration as 1s. And we come back and we see what we made in our table here. We see that the 1s sublevel will hold up to 2 electrons. And so we'd write the electron configuration as 1s2. And again, it's not 1s squared, it's 1s2 is the way it's read. This tells us there's 2 electrons in the 1s sublevel. Then we go on to lithium. Lithium has an atomic number of 3. So this means it has 3 electrons. So writing out its configuration, we start as 1s2. We can't put any more than 2 electrons in the 1s sublevel. And what we're looking at specifically here when we write these out is something called the building up principle. And the building up principle basically says we're going to place electrons in their lowest state of potential energy first, and then we're going to build up from the nucleus and go out. So the building up principle tells us that we start by placing electrons into their lowest possible state of potential energy, and then we build out from there. So once we get 2 electrons into the 1s sublevel, the next sublevel that comes after the 1s is going to be the 2s. And the 2s sublevel, now we only need 1 more electron. So the sum of these superscripts sum to give us the number of electrons in the atom. So 2 plus 1 gives us 3 electrons. And this tells us in an atom of lithium, we have 1 electron in a 2s sublevel and 2 of them in a 1s sublevel. And we read it as 1s2, 2s1. And this is because the atomic number is 3. Let's go on to nitrogen. What is the atomic number for nitrogen? Which means it has 7 electrons. So writing out its configuration, we write 1s2, 2s2. And I know to stop at 2 because the 2s sublevel holds up to a maximum of 2 electrons. And after we fill up the 2s, we go on to the 2p. Well, now the 2p can hold up to 6 electrons. But how many more do we need to fit in here? Just 3. So we'd end this with a 2p3. If we then look at sodium, sodium has how many electrons? 11. So now with 11 electrons right here, we go ahead and place these in. We put in 1s2, 2s2, 2p. Now we'll hold up to 6 electrons. So put in 2p6. Now how many have we accounted for altogether? 10. And we need one more. That next one is going to go into the 3s sublevel. So then we'd end this with 3s1. Now there's a reason why we're looking at this many. Just bear with us. Next one, we have an atomic number of how much? 15. Which means it has 15 electrons. So you put in 1s2, 2s2, 2p6. The 3s sublevel now will hold up to 2 electrons. So we can go up to 3s2, which now gives us a total of 12. We need how many more? 3 more. And the next sublevel available is the 3p. So we put in 3p and put in a 3p3 here to tell us that 3 electrons go into the 3p sublevel. And so now again, if you sum together the superscripts will give us 15, which matches the number of electrons. Then we go on to potassium, which has an atomic number of 19, which means it has 19 electrons altogether. We start out 1s2, 2s2, 2p6, 3s2, 3p6, because the p sublevel now holds up to 6 electrons. And after 3p, we are going to go with
3D.
and we'd love to go with 3d, but we're going to go with 4s, and it's going to be 4s1. Now I'm sure you thought you had the pattern figured out, but looks like many of us didn't. And that's because we have to go back to where we started today. If we go back to where we started today, we were filling out this page right here. And we said that there were 2 main factors that determine the energies of the electrons found in orbitals. They are the size and the shape. Well, it turns out what happens now, if we start analyzing this, and this goes on to our last page here, remember that electrons that are in an s orbital are very, very simple shape. Electrons that go into d orbital are in orbitals that are of a complex shape. So now if you start looking at this figure here representing distance from the nucleus, right here in terms of increasing energy, this portion here representing distance, so this here is distance, you can still think on the average that the distance increases as you go away, when n is equal to 1, 2, 3, 4, and so on. But what happens is this. Now, these over on this side, these aren't so much in terms of distance. This scale here should actually be over on this side right here. These here represent increasing energy. So what happens then is that the 4s sublevel, even though it's part of the 4th energy level that's further away from the nucleus, because its shape is very simple, it actually gives it less energy than the 3d. So the 3rd energy level is closer, but if they are d orbitals, the d orbitals are very complex. So as a result, then, in terms of energy, the 4s sublevel actually has less energy than the 3d. And consequently, electrons go into the 4s first before we start filling up the 3d. So if we then went on from here, let's say we went on to something like arsenic. Arsenic now, which has an atomic number of 33, and we wanted to write out this configuration. what we do is write a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. They go then next into the 4s sublevel like we started. S's will always hold up to 2 electrons. And then after the 4s is going to come the 3d. The d's are going to hold up to how many electrons? We'll hold up to 10. Here's your 3d. We'll now hold up to 10 electrons. So put in 3d10. And now if you start adding superscripts together, we have 2. This makes 4, 10, 12, 18, 20. Plus 10 more gives us 30. We need 3 more. And after the 3d is going to come the 4p. And how many more do we need here? We need 3 more. We'd end with a 4p3. Well, after this point, the overlapping only gets worse because now we start introducing f orbitals and such. If you want to figure out the order in which those sublevels are filled, that's what these arrows are for. You write in these arrows here, descending from here. This is now just a mnemonic. This is a memory aid. If you stack all the 1s's up like this, remember p's don't start till the second level. Stack them all up like this. Remember d's don't start till the third level. Stack them up like this. F's don't start till the fourth level. They stack them like this. Remember the fifth energy level would have out to 5G. 6's would have 6F, 6G, and 6H. This order now would tell us the order in which those sublevels are filled. And if we followed those arrows down, we just go 1s, 2s, 2p, and 3s, then 3p, 4s, then 3d, 5p, and after the, 4p, after the 4p is filled, then we're going to fill the 5s. And then you wind up seeing that order written right here. And that is the order in which those sublevels are going to be filled. Now, of course, once we start getting up to this point, we see we're only up to 33 electrons. You can imagine once we get down to something like lead, those electron configurations get to be super, super, super wide. So I'm going to come in here on Wednesday. We're going to look at some shortcuts for doing this. Any questions? All right. Thank you, folks.